everybody. So we should have just gotten done with doing our little Mr. Covey magic and seeing how inverses are something that kind of undo a function. They undo whatever the original did. Okay. We're going to explore some more ideas with inverses, and we're actually going to see the algebraic process for determining an inverse. First, I just want to talk about a really simple function, 2x plus 1. And let's pause real quick and make a table for that. So plug in -3 for x. 2 times -3 is -6. -6 plus 1 is -5. Okay, we're just subbing in here, filling out a table. Okay, go ahead and finish up that table. Okay, that's what we should have gotten here. And we can graph this. Okay, it's 2x plus 1. You might remember what this graph looks like anyway. It's got a y-intercept of 1 and a slope of 2. So if you plot all those points we have down here, -3, -5, 3, 4, 5, -2, -3. Oh yeah, it matches up with what we thought, which is y-intercept of 1, slope of 2. Then we get this line. Check. Cool. I want to think about this function in terms of what it does to each input. So if you look at this equation, this function, you put in an x value. And what's the first thing it does? Well, it multiplies it by 2. And then it adds 1. So if I was going to write out the steps for what this function does, the first step would be it multiplies by 2. Second step would be it adds 1. So if we want to reverse the map to write the inverse, we have to undo those two things. So instead of multiplying by 2, we have to divide by 2. And instead of adding 1, we have to subtract 1. But we also have to flip-flop the order. So we actually have to subtract 1 first, and then we have to divide by 2. And that's what we should have gotten out of that Mr. Covey magic thing. So I'm going to write a function now, an inverse function. I'm going to use my fancy notation. I'm going to call it f with a little -1. That right there is to indicate that it's the function that undoes the original function f. So you want to make sure you use the same letters so that you know that they're connected, but you put the little -1 so that you know that it's kind of like the opposite of it. Not exactly the opposite, but that's kind of the idea. It undoes it. Okay. So this function is going to take an x. What's it going to do first? Subtract 1. Then it's going to divide by 2. There we go. Let's fill out a table for this function, for our inverse, for f inverse of x. Okay, so let's plug it in. -5 minus 1 is -6, divided by 2 is -3. -3 minus 1 is -4, -4 divided by 2 is -2. Fill out this table for the rest of these, please. Okay, that's what we should get for our table. Okay. Now I want you to take a couple minutes and answer questions 1 and 2. Okay? Take a minute. I want you to look up at what we graphed up here. Look at what we graphed down here. Sorry, what our tables. And I want you to try to answer questions 1 and 2. Okay, pause and take a minute to do that. Okay, so you should have noticed that what we picked for the inputs in this table happened to be the outputs in our original. Okay, and that wasn't a coincidence. That helped us see the idea that what happened to each point on the original, well, -5, let's start the original. -3, -5 was a point on the original. So that on the inverse, you have -5, -3. And since -3 or -2, -3 was a point on f of x, -3, -2 is a point on the inverse. So you notice all of those points, the x and the y, flip. That's always going to be true of a function in its inverse. Your inputs and your outputs flip, your x's and your y's flip. Okay, so that's one big thing to note about inverses. The x's and y's flip. And we're going to come back to that idea. Can you go ahead and pause and graph these points on the same axis up here? So pause and go ahead and graph those on the same graph. Oh, so that red graph that we had originally was our function f of x, and this blue one was the inverse. I just got those points from the table down there. And what you notice is those graphs are different, and the connection between them is kind of weird. It's kind of hard to see. But if you look at that dotted line I drew in, you can see that dotted line kind of acts like a line of symmetry. In other words, if you flipped the red one over that pink line, you'd get the blue one. The way we say that is a function and its inverse are symmetric over that pink line. And if you remember that pink line, if you look at it, it's the simplest line. It just goes up 1 over 1. They're symmetric over y equals x. Okay? That's that line they're symmetric over. So a function and its inverse, their graphs are connected. They're symmetric over y equals x. So you can look at two graphs and tell if those functions are inverse of each other. All right, moving on. Flip the page. Back to that idea of inverses have their x and their y's flip. That's really the core idea behind inverses. And so that has a couple results. First is this, and this is a little confusing, but if you think about it for a second, it makes sense. If you have a function f of x, and you think about the inputs as being the domain, and the outputs as being the range. Okay, the input stuff, and you get your outputs. Your inputs are called domain, your outputs are called range. You guys know that. And you think about the inverse of that function, which undoes it, kind of forms a circle. You do one, and then you undo it. And you end up back where you started. It kind of makes a circle. But if you look at that inverse function, well, what you put into that inverse function is this bubble. So that's the domain for the inverse. And what you get out is this bubble, which is the range for the inverse. But you'll notice those bubbles are like the same. Like those things are both this bubble and both those things are that bubble. In other words, the domain of the original is the range of the inverse. The x's and the y's flip. The range of the original function is the domain of the inverse function. The domain and range flip. The x and the y's flip. If you go back to the table, that's exactly what's happening here. What were these in the original? Well, these were the domain of f of x, and those become the range of the inverse. The range of the original becomes the domain of the inverse. Everything's flip-flopping. X's and Y's are flip-flopping. Okay? That's why they undo each other. It's good to think about it as a circle. You do something, then you undo it. You add 5, and then you subtract 5. You're back to where you started. There's an algebraic way to find inverses. And the reason this exists is because when you look at complicated equations, maybe you were even confused here with this one. This was a little tricky. But when you look at increasingly complicated equations, figuring out the inverse, it's hard to do this process here. It's hard to do Mr. Kirby magic, okay? There's an actual series of steps you can follow to find the inverse. So these are steps for finding an inverse, and here's how it works. Step 1, replace f of x with, what do you think I'm going to say here? What's f of x the same as? Well, f of x is fancy function notation, but it's the same as just your output. It's the same as your y. So first step is, if it's written with this fancy function notation, replace the f of x with y. Second step is the key step. You flip x and y. Everywhere there was an x, you put a y. Everywhere there was a y, you put an x. You flip the x and the y. Lastly, you solve for y. And you need to know these 3 steps. These are the 3 steps for finding an inverse. All right, so actually let's do a couple of these, okay? First one's easy because it's a simple function, but I want to go through the process of these. So we have a function here, f of x equals x plus 2. We want to find what function would undo that function. Now, I'm going to replace the f of x with a y. Okay, just because this xy notation is easier to work with than the fancy function notation. Then, the key step, I'm going to flip the x and the y. So instead of writing y equals, I'm going to write x equals. Instead of writing x plus 2, I'm going to write y plus 2. It flips the x and the y, and the last step is to solve for the y. Remember when I say solve for the y, I mean get the y by itself. That's what solving for the y means. Get the y by itself. How do I get this y by itself? Well, I subtract 2 from both sides. So I end up getting x minus 2 equals y. It's important at the end of the day, too, I should almost have this as a step, to write it in that fancy function notation. So what I just found was f inverse of x. Remember that little fancy -1 up there tells you that the thing you're talking about, it undoes f of x. It's the opposite of it, undoes it. If you look at that answer, makes a lot of sense, right? This function was x plus 2. How do you undo x plus 2? Well, you do x minus 2. Let's do one more together, and then I'll let you guys do a couple. Here's f of x. I'm going to write it with a y. And the inverse. Flip the x and the y. And I'm going to get the y by itself. A few different ways to do this. I think that you guys would be more comfortable distributing that, maybe? Not sure. Lots of different ways to do that. Let's distribute it. And I'm trying to get the y by itself. Well, that's -3 plus 5. That's just plus 2. Trying to get the y by itself. I'm going to subtract the 2. And lastly, I'm going to divide both sides by 3. There. There's my inverse function. It'd be nice to write it in that fancy little inverse notation. Again, the reason these steps exist is because it's kind of hard to look at this original function and then figure out that this would be the inverse. That's pretty hard. That's why this algebra exists. Okay. I want you to go ahead and pause and give these next two a try. Okay. Follow our 3 steps up above. Don't forget. Okay. Give those two a try. Okay, so those blue ones were what I got for the inverses of those 2 functions. Okay, so you can pause and take a look at that work if you want. And I just want to do one more thing here. I want to do a little bit more of this graphing thing real quick. Let's just do, yeah, let's do this one. This one's a little more fun. Okay, so I want to take this function, g of x equals x cubed, and I want to make a table for g of x, and then make a table for its inverse based on what we know about a function that's inverse. Okay, so we're going to make a table for g of x. This will be not too bad. Let's pick some x values. Let's just do -2, -1, 0, 1, 2. What's -2 cubed? -2 times -2 times -2? I mean -8. -1 cubed, -1 times -1 times -1 is going to be +1. Excuse me, -1. Come on, Mr. Freddy. 0 cubed, 0. 1 cubed, 1. 2 cubed, 8. Okay. So for the original g of x, we get a graph that looks like this. -2, -8. And you might remember this graph a little bit from Algebra 2. It's kind of a weird little squiggly thing. It looks something like that. That's what an x cubed graph looks like. Okay. So to make a table for its inverse, we could find the inverse algebraically and then plug it all over. That's a lot of work. Instead, just remember that the x's and the y's flip. Okay, remember these are our y's. Our x's and our y's flip. So on the inverse, I'm going to have not -2, -8. I'm going to have -8, -2. That point's going to stay the same. That point's going to stay the same. That point's going to stay the same, coincidentally. And then I'm going to have 8, 2. Okay, so if we plot these points, we see this graph. And it's kind of weird what happens in there, but it's something like that. Okay, so the red graph is g of x, and the black graph is its inverse. And you'll notice it has that relationship we talked about before. They are symmetric over that straight diagonal line. In other words, I should draw that better. If you draw that diagonal, y equals x, and you look at that black and that red graph, they're symmetrical over that. They flip over and they match up with each other. That concludes this video about inverses. Thanks for watching, guys.